Part 1. A faint signal from deep space. Scientists have just revealed a discovery so groundbreaking it completely reshapes what we thought we knew about the interstellar object 3I Atlas. Barely 2 weeks ago, on October 24, they detected something that had never before happened in the entire history of radio astronomy. 3I Atlas emitted a radio signature while passing through our solar system. The detection was confirmed. The chemistry was real. Hydroxyl radicals, water breaking apart under starlight. But what keeps researchers awake at night is this. The signal came from the same patch of sky as the infamous WOW signal of 1977. And that's not even counting the 8 other documented anomalies, the unexplained deviations in its trajectory, and the detection window so narrow we nearly missed it altogether. Stay with me, because by the end of this nocturnal exploration, you'll see why this discovery changes everything. If these developments fascinate you as much as they do me, make sure to like and subscribe so you don't miss a single update as this unfolds in real time. Leave a comment telling us where you're watching from, what time it is there, and what you think about this new discovery. You're the reason we can keep chasing stories like this. Thank you for being a part of it. October 24th, 2025. 4:10 a.m. UTC. Most of South Africa still slept beneath a blanket of stars, the kind of darkness that makes you feel as if you're standing at the edge of infinity. But in the Karoo Desert, 64 massive radio dishes remained awake, their silvered surfaces tilted toward a patch of sky so close to the sun that observing it bordered on the impossible. The Meerkat Radio Telescope Array, one of the most sensitive radio instruments humanity has ever built, was doing what it does best, listening to the whispers of the cosmos. And on that particular dawn, it heard something that shouldn't have been there. 2 absorption lines appeared in the data stream. Faint, yes, barely distinguishable from the cosmic hiss of the universe, but structured, deliberate. The frequencies were exact, 1665 MHz and 1667 MHz. If you know anything about radio astronomy, those numbers should quicken your pulse. They're the hallmark lines of hydroxyl radicals, the OH molecule, a chemical fingerprint that forms when water breaks apart under ultraviolet radiation. This wasn't static. It wasn't a passing satellite or a hardware glitch. It was chemistry, broadcast across hundreds of millions of miles of empty space, and it came from something that absolutely did not belong to our solar system. The object in question was designated 3I Atlas, catalog number C/2025N1. The I stood for Interstellar, the 3rd confirmed visitor from beyond the Sun's gravitational frontier. It had been discovered earlier that year, plunging inward on a hyperbolic trajectory that screamed outsider. Astronomers had tracked it for months, watching it brighten as it approached perihelion, the point closest to the Sun. They had measured its velocity, mapped its orbit, analyzed the formation of its tail, documented its variations in brightness, but no one, not a single person on Earth, had ever detected a radio signal from an interstellar object before. Not once. In the entire history of radio astronomy, going back to the 1930s when Carl Jansky first detected radio waves from the Milky Way, nothing like this had ever occurred. Let's be perfectly clear about what hydroxyl radicals mean. When water molecules are struck by ultraviolet radiation from a star, they don't simply evaporate peacefully. They shatter. The hydrogen atoms go flying off in one direction, while the hydroxyl radicals, those ghost-like OH fragments, linger behind. They absorb very specific wavelengths of radiation, creating dips in the spectrum, precisely at 1665 and 1667 megahertz. It's one of the most fundamental chemical signatures of water in the universe, the same chemistry that makes life possible on Earth. Every drop of water in your body, every molecule that makes up roughly 70% of you, can break into these same radicals under the right conditions. So when astronomers see hydroxyl absorption lines in space, they're looking at the fingerprints of H2O, the universal solvent, the liquid that made biology possible. But here's where it gets strange. This wasn't a random detection from some comet in the outer solar system, or a distant star-forming nebula. This came from 3I Atlas, an object that had spent millions, perhaps billions of years drifting through the lightless void between stars, carrying who knows what kind of ice and organic compounds on its surface. Now, as it passed near our sun, it was releasing those volatiles, and for the first time, our radio telescopes could glimpse its true chemistry. For the first time in human history, we were obtaining direct chemical information from interstellar material, not by sending a probe to collect dust, but by listening to the faint radio whispers of molecules breaking apart in real time. The scientists who first saw the data did what scientists always do. They doubted. They compared the signal against radio frequency interference databases. They checked for satellites in the area. They cross-referenced the detection time with known sources of terrestrial noise. They even reviewed 2 prior observation attempts, September 20th and September 28th, both of which showed nothing. No signal, no hydroxyl, just silence. So why October 24th? What changed? The answer, it turned out, came down to geometry and timing, 2 factors that made this detection not just rare, but almost cosmically improbable. Then, someone noticed something else, something that sent a ripple of unease through the astronomical community. The kind of coincidence that makes even the most rational scientists pause and wonder if the universe has a sense of humor. The celestial coordinates where 3I Atlas was located at the moment of detection, the exact patch of sky from which those hydroxyl lines emerged, fell uncomfortably close to another famous location, a region that, 48 years earlier, had produced the most iconic unexplained radio signal in the history of the search for extraterrestrial intelligence. You probably know it by its nickname, the WOW signal. August 15, 1977. The Big Ear radio telescope in Ohio caught a narrow-band signal so strong, so precisely structured, that astronomer Jerry Eman circled it on the printout and wrote "Wow" in the margin. It lasted 72 seconds and never repeated. It came from the constellation Sagittarius, and despite decades of follow-up observations, no one has ever definitively explained it. Was it alien? A comet? Some strange astrophysical event we don't yet understand? The question remains open. Now, almost half a century later, another interstellar mystery was unfolding in nearly the same patch of sky, separated by only 9 degrees of arc, close enough to make you wonder whether something about that region draws strange signals the way a flame draws moths. Let's be clear, this isn't a message. No one is claiming 3I Atlas is broadcasting a greeting or sending us a cosmic encyclopedia. The signal is an absorption line, not a transmission. It's chemistry, not communication. Yet the structure, the precision, the sheer improbability of detecting it, combined with the eerie echo of the WOW signal, has created a perfect storm of speculation. Online forums lit up. SETI researchers began drafting observation proposals. Popular media splashed headlines about interstellar whispers and alien chemistry. And in the background, scientists kept doing what they do best: measuring, calculating, ruling out the impossible, and trying to explain the improbable. Part 2. The chemical language of the cosmos. Decoding the hydroxyl radicals. Here's the thing, you can't just point a radio telescope at any interstellar object and expect to pick up hydroxyl. The chemistry has to be there, yes, but the geometry must also be perfect. Hydroxyl radicals don't shine like stars or galaxies. They absorb light. That means you need a background source, something bright behind the target, so the hydroxyl molecules can block specific wavelengths and carve those telltale absorption lines into the spectrum. In the case of 3I Atlas on October 24, that background source was the Sun. The comet had approached close enough, and its position in the sky aligned just right, so that sunlight passed through its coma, the diffuse cloud of gas and dust surrounding its nucleus. As the Sun's ultraviolet radiation struck the water molecules sublimating from the comet's icy surface, it tore them apart. Hydrogen flew one way, oxygen another, and hydroxyl radicals floated in between, absorbing radio photons at those characteristic frequencies. But the observation window was brutally narrow, too far from the Sun, and the comet wouldn't release enough volatiles to create a detectable signal. Too close, and solar glare would overwhelm the radio telescopes. The astronomers had to time it precisely, observing during those brief pre-dawn hours when the Sun was still below the horizon, but 3I Atlas had already risen high enough to track. They almost missed it. Almost. The two earlier attempts on September 20 and September 28 had come too soon. The comet was still too distant, its gas production too low. By October 24, it had crossed the threshold. Sublimation had intensified. The coma had expanded, and for a fleeting moment, perhaps just a few hours in the history of the universe, the conditions were exactly right for us to hear the water of another star system breaking apart in real time. Think about that. Of all the interstellar objects that have crossed our solar system over billions of years, most invisible to us because we lacked the technology, this one, this single frozen wanderer from deep space, passed through during the tiny sliver of human history when we possessed radio telescopes sensitive enough to hear its chemistry. It came close enough to the Sun to spark a signal, and aligned with our line of sight so precisely that we could see those absorption lines against the solar background. The odds of that happening are astronomical. Literally. And yet it did, which raises the question haunting astronomers ever since the detection. Was it really luck? Or are we missing something fundamental about how these objects behave? Because 3I Atlas isn't the first interstellar object we've found. It's the third. The first was 1I/Oumuamua, which shot through the inner solar system in October 2017, moving so fast and at such an odd angle that astronomers nearly missed it entirely. By the time they realized what it was already on its way out, moving too quickly for any spacecraft to catch up. It showed no visible tail, no detectable outgassing, and based on how its brightness varied, its shape appeared strangely elongated, like a cigar, a flat disk, or something that didn't quite fit any known category. And then there was its acceleration. As Oumuamua moved away from the Sun, it sped up slightly, faster than gravity alone should have allowed. The effect was small, but measurable. The only reasonable explanation was that it was venting gas, expelling volatile material from its surface like a tiny thruster. But if that were true, where was the tail? Where was the dust, the gas cloud that should have been visible? No one could see it. Avi Loeb, chair of Harvard's astronomy department, proposed a provocative alternative. What if Oumuamua wasn't a comet at all? What if it was artificial? A solar sail, perhaps, built by an extraterrestrial civilization and drifting through the galaxy, propelled by the pressure of starlight. The idea was controversial, speculative, and most astronomers dismissed it. Yet, it was hard to ignore that Oumuamua behaved like nothing we had ever observed before. Then came 2I Borisov in August 2019, unmistakably a comet. It had a bright, diffused tail and all the classic signs of outgassing. Its spectrum revealed cyanogen and diatomic carbon, organic molecules common in comets from our own solar system. It was comfortingly normal, and astronomers breathed a collective sigh of relief. Maybe Oumuamua was just the outlier. Maybe most interstellar visitors were simply icy messengers, carrying frozen water and organics from one stellar system to another, not unlike the comets orbiting our own sun. And then came 3I Atlas. Another comet, yes, but one with its own peculiarities, because while Borisov behaved predictably, obeying the laws of gravity and cometary physics without surprises, 3I Atlas showed anomalies, subtle but undeniable, small deviations in its trajectory that didn't fit perfectly into orbital models, variations in brightness, suggesting something more complex than simple outgassing. And now this radio detection, the first of its kind, confirming it carried water, but raising new questions about why it could only be detected in such a narrow window of time. 3 interstellar objects, 3 utterly different personalities. Oumuamua, the tailless enigma that accelerated inexplicably. Borisov, the textbook comet that behaved exactly as expected. 3I Atlas, the water-bearer that whispered in radio frequencies for a brief moment before vanishing back into silence. So what does that tell us about the population of interstellar objects as a whole? If the first 3 we've found are so different from one another, what does that mean for the thousands or millions we haven't yet seen? Is every interstellar visitor unique, shaped by the conditions of its home system? Or are there families, categories of objects with shared traits that we simply haven't observed enough to recognize yet? These are the questions that keep planetary scientists awake at night. With only 3 data points, you can't draw a curve, you can't build a theory. All you can do is speculate, observe, and hope the next visitor delivers the missing piece that makes everything click. But let's circle back to the signal, to those 2 absorption lines at 1665 and 1667 MHz. What do they actually tell us about 3I Atlas? First, they confirm the object carries water, not mere traces, but in substantial quantities, enough that when the sun heats its surface and the ice sublimates directly into gas, the resulting cloud of vapor becomes dense enough to produce a radio-detectable signal across 93 million miles of space. That's extraordinary. It means 3I Atlas, despite spending eons drifting through the near absolute zero chill of interstellar space, retained its ice. It didn't evaporate. It didn't outgas. It stayed frozen, waiting until the sun's gravity pulled it in and the star's warmth finally woke it. Second, those absorption lines reveal something about the physics of the coma. Hydroxyl radicals don't last long. They're reactive, unstable. They recombine quickly with other atoms or get photodissociated by more ultraviolet light. The fact that we detected them at all means they were being produced continuously, a steady stream of fresh water molecules breaking apart to replace those destroyed. That implies active, sustained outgassing, at least during the period of observation. Third, and perhaps most intriguing, the detection raises the possibility that other interstellar objects may also have produced hydroxyl signals, but we simply weren't listening. Oumuamua passed through during a time when radio telescopes weren't routinely scanning small solar system bodies. Borisov was observed extensively, but mainly in optical and infrared wavelengths. Did anyone check for radio emissions? Did anyone look specifically for hydroxyl lines near its perihelion? The answer is complicated. Some radio observations were indeed made, but not with the kind of sensitivity or time coverage applied to 3I Atlas. And that's the most important lesson of all. You can't find what you're not looking for. Part 3. The Echo of the WOW Signal. For decades, the WOW signal has stood as the holy grail of the search for extraterrestrial intelligence. A brief, intense, inexplicable burst of radio waves that appeared exactly where nothing should have been, and then it disappeared, leaving no trace, never repeating despite countless follow-up attempts. Skeptics argued it must have been terrestrial interference, a passing satellite, or an atmospheric reflection quirk. Believers countered that it was too clean, too structured, too perfectly tuned to the neutral hydrogen band, the frequency astronomers have long speculated other civilizations might use because it's universal and recognizable to any species that studies the cosmos. 48 years later, 3I Atlas popped up in the same general region of the sky. Not at the precise coordinates. The WOW signal came from right ascension 19H25 midids 31 seconds plus or minus 10 seconds and declination minus 26 degrees 57, while 3I Atlas was detected about 9 degrees away. But in cosmic terms, that's practically the same neighborhood, like living on the same block rather than in the same house. So, is that meaningful? Or just a coincidence? The honest answer is that no one knows. The sky is big, truly big. It covers about 41,253 square degrees of area, and the region around Sagittarius, where both the WOW signal and 3I Atlas were detected, is not especially distinctive from an astronomical standpoint. It points toward the galactic center, yes, which means there are lots of stars in that direction, but that's also true for any line of sight along the galactic plane. The odds that two rare events occur within the same 9-degree separation purely by chance aren't as astronomically small as you might think. If you pick one random point on the sky and then another, the probability that they lie within 9 degrees of each other is about 0.6%. Roughly 1 in 160. Not common, but not miraculous either. Over thousands of astronomical detections, you'd expect to see a few such coincidences by chance alone. Here's the catch that makes this particular coincidence more unsettling than most. Both events involve radio signals. Both are unusual. Both resisted simple explanations when they were first detected, and both look toward the Milky Way's crowded heart, where stellar systems are most densely packed. Before imaginations run away with the story, let's be clear about what scientists are not saying. No one is arguing that 3I Atlas is artificial. No one is suggesting it was deliberately aimed at our solar system. No one claims the hydroxyl signature is a coded message. The chemistry is straightforward, water breaking under starlight. That's all. Even so, the juxtaposition is odd enough to merit attention, and it has reignited the debate about what the WOW signal actually was. One of the most recent and widely discussed explanations was proposed in 2017 by Antonio Paris, a professor of astronomy at St. Petersburg College in Florida. He suggested that the WOW signal could have been caused by a comet, specifically 266P Christensen, that would have been in the right patch of sky in August 1977 to produce hydrogen emission. Comets can shed hydrogen clouds as they near the Sun, and neutral hydrogen emits at 1420 MHz, close to the WOW frequency. The idea was met with skepticism. Jerry Eman, the astronomer who originally detected the WOW signal, publicly rejected the comet hypothesis, noting that the signal was too narrow in bandwidth, too precise in frequency, and too brief in duration to match what a comet would produce. Other astronomers pointed out that thousands of comets have been observed over the years, and none has generated a radio signal anything like WOW. Still, the comet hypothesis lingered in the public imagination, in part because it offered a natural workaday explanation for something otherwise mysterious. And now, with 3I Atlas producing detectable radio features as it passes perihelion, the idea has gained new traction. Could the WOW signal have been an interstellar visitor? Not 266P/Christensen, which is an ordinary solar system comet, but something from outside. Something like 3I Atlas, that swept through our neighborhood in 1977 and produced a brief burst of radio emission before vanishing into deep space. It's a tempting notion. It fits the fact that the signal never repeated, because an interstellar object on a hyperbolic path would pass only once. It explains the brevity, because the observation window for such events is incredibly narrow, and it supplies a natural mechanism for radio emission without invoking alien intelligence. But there are problems with this explanation too. First, the WOW event was emission, not absorption. It transmitted energy instead of blocking it. Hydroxyl radicals produce absorption lines, as we saw with 3I Atlas. To yield emission, you'd need a different mechanism, perhaps hydrogen atoms or molecules excited by ultraviolet radiation, or some other maser-like process we don't yet fully understand. Second, if interstellar objects routinely produce detectable radio signals, why haven't we seen more? We've confirmed 3 interstellar visitors so far: Oumuamua, Borisov, and 3I Atlas. Only one produced a detectable radio signature. If WOW was caused by an interstellar passerby, that would imply such signals are rare even among interstellar objects, which makes the 1977 detection even more unlikely. Third, and this is what really keeps astronomers awake, there are 8 other anomalies in the WOW region that have been documented in the years since. Not as dramatic as the original, but odd enough to mention. Brief spikes that don't fit neatly into any category. Patterns of noise that look almost, but not quite, random. Nothing as compelling as the original WOW event, yet enough to make you wonder whether there is something about that region we don't yet grasp. Could it be an interstellar traffic corridor, a route that objects tend to follow because of the galaxy's gravitational currents? Some kind of focusing effect, where the Milky Way's gravitational field concentrates objects from certain orbits into particular directions, like light passing through a lens? Or, and here's where things turn truly speculative, could there be something in that region that emits signals periodically, something we caught in 1977, and then again, in a different guise, in 2025? Before you file that under science fiction, consider this. There are natural objects in the universe that produce periodic radio signals. Pulsars, for instance, are rapidly spinning neutron stars that sweep beams of radiation like a cosmic lighthouse. When the beam points toward Earth, we detect a pulse. When it points away, we see nothing. Some pulsars have millisecond periods, others tick every few seconds. A handful of the slowest stretch to many seconds or even minutes. What if there are even more exotic, as yet undiscovered sources that emit radio bursts on timescales of years or decades? You'd detect a flare, then nothing for a long time, and then, if luck holds, another. From our vantage point, it would seem random and unpredictable, yet in reality it could be perfectly periodic, simply operating on a cadence beyond our current ability to monitor continuously. That is pure speculation, of course. There is no evidence for such objects, yet. But the universe has a habit of being stranger than we expect, and the history of astronomy is full of discoveries that sounded like science fiction until they proved to be real. In the meantime, scientists are doing what they do best: observing, measuring, building models, and testing them against the data. The Meerkat radio array that detected 3I Atlas is now on the watch list for the next interstellar visitor. When another appears, and one will, astronomers will be ready to aim every instrument available: radio, optical, infrared, ultraviolet, the full spectrum. We want to know whether radio signatures are common or rare, whether hydroxyl lines always appear or only under specific combinations of illumination, geometry, and gas production rate, and whether any patterns emerge in timing, intensity, or frequency. And perhaps, just perhaps, eventually we'll understand these objects well enough to look back at 1977 and say with confidence, yes, that is what the WOW signal was. Not a message from aliens, not an equipment glitch, just another interstellar passerby slipping past and leaving a radio whisper we mistook for something more. Or perhaps not. Perhaps the WOW signal will remain forever unexplained, a reminder that the universe keeps its secrets, and that no matter how advanced our tools become, there will always be mysteries that resist our understanding. Part 4. The Gravitational Dance, Trajectory and Fate of 3I Atlas. Let's talk about the orbit of 3I Atlas, because that's where things become truly mind-bending. This is not an object that circles our sun like the planets, asteroids, and comets born here. It's a visitor, a cosmic vagabond on a path that proclaims its foreign origin with every mile it travels. Astronomers describe orbits using a quantity called eccentricity. It's a number that tells you how stretched or circular an orbit is. An eccentricity of 0 means a perfect circle. The planets in our solar system range from about 0.01 to 0.2 nearly circular paths that keep their distance from the sun relatively stable throughout the year. Long-period comets, those that spend most of their time in the outer regions and plunge toward the sun once every few centuries or millennia, have eccentricities close to 1, elongated ellipses that carry them from the icy depths beyond Neptune to the scorching inner system. But 3I Atlas has an eccentricity greater than 1, specifically around 1.045. That means its orbit isn't an ellipse at all. It's a hyperbola, an open curve that never closes. It entered our solar system from interstellar space, looped around the sun, and is now on its way out, accelerating as it goes, and it will never, ever return. Unless something stops it. I-Atlas moves at about 26 miles per second relative to the sun, roughly 94,000 miles per hour. At that speed, you could travel from Earth to the Moon in under 3 hours. You could cross the entire continental United States in a little over a minute, and 3I Atlas has been cruising at that velocity, or faster, for millions of years, crossing the emptiness between the stars. Where did it come from? That's where things get complicated. You can't just trace its path backward and point to a specific star and say, there, that's home. Interstellar space isn't empty. It's filled with faint gravitational fields from stars, rogue planets, gas clouds, and dark matter. A web of invisible forces that tug and twist objects as they travel. Over millions of years, those tiny nudges add up. The trajectory bends. The origin blurs. Astronomers have tried to backtrack the orbits of Oumuamua, Borisov, and 3I Atlas to see where they might have come from. Oumuamua, the first, appeared to arrive from the general direction of Vega, the bright star in Lyra, but once you account for Vega's motion through the galaxy, the timelines don't match. Vega wasn't in the right position millions of years ago when Oumuamua would have begun its journey. Borisov seemed to come from the direction of Kruger 60, a binary star system about 13 light-years away. But again, when stellar motions are considered, the link falls apart. It's not impossible that Borisov originated there, but there's no solid proof. As for 3I Atlas, its backward calculation is even murkier. Its path points vaguely toward Sagittarius, near the galactic center, but that's like saying it came from somewhere over there. Millions of stars fill that patch of sky. Identifying which one, if any, ejected this object is currently impossible. Here's the fascinating part. Even if we can't pinpoint where it came from, we can estimate how long it has been traveling. The answer is likely millions of years, possibly tens of millions. At 26 miles per second, 3I Atlas would take about 300,000 years to travel just 1 light year. The nearest star, Proxima Centauri, lies 4.24 light years away. That's more than 1 million years of travel. If 3I Atlas came from farther out, and statistically it likely did, then it may have been adrift for 10, 20, even 50 million years. Through all that time, it was alone. No sunlight to warm its surface, no planetary gravity to alter its course, only cold, darkness, and the faint whisper of the cosmic microwave background washing over it as it drifted. Any volatile compounds near its surface, anything that could sublimate easily, would have long since vanished. What remains are the deepest, most stable ices, protected by insulating layers of dust and rock. And then, by sheer accident of galactic geometry, its path intersected ours. It wasn't pulled here. It wasn't aimed. It just happened, the same way 2 cars traveling on perpendicular roads might cross an intersection if the timing is just right. The sun's gravity caught 3I Atlas and bent its path. Not enough to capture it, not enough to make it a permanent member of our solar family, but enough to alter its velocity and heading. The object dove inward, accelerating as it neared perihelion. At its closest, roughly 37 million miles from the Sun, about 40% of Earth's orbital distance, it was briefly bathed in fierce sunlight. Ice on its surface began to sublimate. A tail formed, and during that precious, narrow window, radio telescopes heard the faint whisper of water breaking apart into hydroxyl radicals. Now it's leaving. Every second, it's another 26 miles farther from the Sun. Every hour, 94,000 miles more distant. By the end of this month, it will be beyond Mars. By year's end, it will have passed the orbit of Jupiter. In a decade, it will be beyond Pluto, entering the Kuiper Belt. Within a century, it will be no more than a faint speck of light at the edge of the solar system, too distant, too dim for any telescope on Earth to track. But it won't stop. It will keep going, slipping beyond the Sun's gravitational reach, regaining its interstellar speed as the star's pull weakens. Eventually, it will return to roughly the velocity it had upon arrival, perhaps slightly altered by its encounter, and then it will once again be free, back in the void, back in the dark. Where is it headed? No one knows. Its current direction points roughly toward Orion, but that's only its present heading. Over the coming millions of years, gravitational nudges from passing stars will alter its path. It might skim another stellar system, get captured into orbit and become a comet around some distant sun. Or it might wander forever, never again finding warmth, never again releasing its hidden water, just drifting until the universe itself grows old and cold. Here's the part that haunts me. Atlas carries something. Organic molecules, complex compounds forged in the gas clouds surrounding its parent star. Maybe amino acids, the building blocks of proteins. Maybe nucleobases, the components of DNA and RNA. We know comets in our own system contain such compounds. We know they can survive for millions of years in the frozen dark. And we know that when comets fall onto planets with atmospheres, they can deliver those molecules intact. So what if 3I Atlas at some distant point in the future, collides with a planet. Not one of ours, we missed that chance, but one orbiting another star somewhere along Orion's arm of the galaxy. It could deliver its cargo of interstellar organics to a world that has never known such chemistry. It could seed that world with the raw ingredients for life. And if that can happen once, it can happen countless times. In fact, it probably already has, across the entire galaxy. Life isn't confined to the planets where it began, it travels. It hitches rides on icy rocks from one stellar system to another. Over billions of years, the chemistry of life may have spread throughout the Milky Way, not through spaceships or radio messages, but through comets, striking the right world at the right time. That idea is called panspermia, the notion that life, or at least its ingredients, can migrate between worlds. It's controversial. Many scientists remain skeptical. But the discovery of interstellar objects like 3I Atlas makes it harder to dismiss, because now we know, not guess, but know, that material moves between star systems. We've seen it, we've measured it, we've even heard its chemistry. Part 5. 3 Visitors, 3 Mysteries, Comparing the Outsiders. If Atlas were the only interstellar object we'd ever detected, it would be impossible to tell what's typical and what's odd. But we now have 3 data points. And while 3 isn't enough to build a full statistical theory of the interstellar population, it's enough to start looking for patterns. Or, in this case, the lack of them. Because the most striking thing about Oumuamua, Borisov, and 3I Atlas is how different they are from one another. Let's start with Oumuamua. Its name in Hawaiian means scout, or messenger that arrives first from afar. Fitting, since it was the first of its kind we ever spotted. It arrived in October 2017, and we nearly missed it altogether. It was moving so fast, over 54 miles per second relative to the Sun, about 194,000 miles per hour, that by the time astronomers realized its orbit was hyperbolic, it was already on its way out, passing Mars's orbit and heading for interstellar space. What made Oumuamua so baffling was its lack of comet-like features. It showed no visible tail, no obvious coma of gas and dust. Its brightness swung dramatically, changing by a factor of 10 over a rotation period of roughly 8 hours, implying a highly elongated shape, perhaps with a length-to-width ratio near 10:1. Picture a cosmic cigar tumbling end over end as it plunged through the inner solar system. But the biggest anomaly was its non-gravitational acceleration. As Oumuamua receded from the Sun, it sped up slightly, about 0.00001% faster than solar gravity alone would predict. Small, but definitive. Something was pushing it, providing an extra nudge. For comets, that's normal. As ice sublimates from a comet's surface, the escaping gas acts like a tiny rocket, pushing the nucleus in the opposite direction. That's outgassing, the reason comets grow tails and show non-gravitational accelerations. But Oumuamua had no detectable tail. No gas or dust was seen venting from it. So what was doing the pushing? Avi Loeb, the Harvard astrophysicist, proposed that Oumuamua might be a solar sail, a thin sheet propelled by the pressure of sunlight. If it were thin enough, only a few millimeters thick, it could experience measurable acceleration from starlight without any need for outgassing. And if it were artificial, crafted by a technological civilization, that could explain its odd shape and anomalous behavior. Loeb's hypothesis triggered instant controversy. Other astronomers argued for more mundane explanations. Perhaps Oumuamua was outgassing, but the volatiles were invisible in optical bands. Hydrogen or nitrogen, for instance. Perhaps its shape wasn't a cigar at all, but a flat disk, a pancake. which could also explain the brightness swings. Perhaps the acceleration came from asymmetric radiation pressure, sunlight reflecting differently across its surface. The debate continues. But one thing is clear. Oumuamua didn't behave like any comet or asteroid we had seen before. It was an outlier, an anomaly that resisted easy categorization. Then came 2I/Borisov in August 2019, discovered by Russian amateur astronomer Gennady Borisov, and it was disappointingly normal, or refreshingly normal, depending on your perspective. Borisov was unequivocally a comet. It sported a bright, diffuse tail, stretching millions of miles behind it. It showed an active coma of gas and dust. Its spectrum revealed cyanogen, Cn, diatomic carbon, C2, and water, H2O, all common molecules in comets of our solar system. Its nucleus was small, likely under 0.6 miles across, and its shape appeared roughly spherical. Its orbit was also hyperbolic, with an eccentricity around 3.36, much higher than Oumuamua or 3I Atlas. That meant it was moving even faster, about 20 miles per second on entry into the solar system, though it slowed while approaching the Sun and sped up again on its way out. Astronomers scrutinized Borisov throughout its inner solar system passage. Telescopes worldwide, including the Hubble Space Telescope, took detailed observations. They measured its composition, outgassing rate, spin period, and albedo. The verdict? It looked strikingly similar to long-period comets from our own system, those that originate in the Oort cloud and visit the inner Sun only once every thousands or millions of years. The one standout difference was Borisov's unusually high carbon monoxide, CO, content relative to water. Most solar system comets are water-dominated, with only small amounts of CO. Borisov was richer in CO, hinting that it formed in a colder region of its natal system, perhaps farther from its star than typical comet birthplaces in our own. Aside from that, Borisov delivered no surprises, no anomalous accelerations, no bizarre shapes, no inexplicable behavior, just a comet doing comet things, ferrying ices and organics from one star system to another. Astronomers exhaled. Maybe Oumuamua was the oddball. Maybe most interstellar objects would be like Borisov, predictable and understandable within the framework of comet science we already know. And then came 3I Atlas. 3I Atlas differs from both Oumuamua and Borisov. It's not as weird as Oumuamua. It hasn't sparked talk of artificial solar sails, but it isn't as straightforward as Borisov either. It has its own quirks, its own mysteries. First, the radio detection. Neither prior interstellar visitor produced a detectable radio signature. Oumuamua blew by too fast and too faint for deep radio work. Borisov was observed at radio wavelengths, but no hydroxyl lines were found. 3I Atlas is the first to reveal its chemistry directly via radio. Why? What's special about 3I Atlas? More water than the others? A closer brush with the Sun that supercharged outgassing? Or did we simply get lucky, watching at the right moment with the right instruments? Second, its trajectory. 3I Atlas has an eccentricity near 1.045 between Oumuamua, approximately 1.20, and Borisov, 3.36. That puts it mid-pack in interstellar speeds, not too fast, not too slow. But its inclination, the angle of its orbit to the ecliptic, is significant, around 45 degrees. That means it arrived from above the solar system, dove through the plane where the planets orbit, swung around the Sun, and then exited on a different angle. That geometry matters. It constrains which parts of the sky we can watch during close approach and it controls how long the object spends where sunlight is intense enough to trigger substantial outgassing. Third, its tail. I-Atlas grew a tail as it neared perihelion, like Borisov, but structurally different. Telescopic observations showed multiple components, regions of differing brightness and composition, suggesting that outgassing wasn't uniform across the surface. Perhaps there were active patches, hot spots where ice was easier to access, alternating with inert regions where a dust mantle insulated the volatiles below. This kind of irregular activity is common in solar system comets, but it's fascinating to see in an interstellar object because it tells us the same physical processes, sunlight, heating, sublimation, dust dynamics, operate regardless of a comet's home system. Fourth, and this is what keeps some researchers up at night, there are hints of trajectory deviations that don't quite match the models. Small, within the error bars, but persistent enough to warrant attention. Are these non-gravitational accelerations from asymmetric outgassing, or something else? Most astronomers would bet on outgassing, the simplest explanation and the one most consistent with what we know. But until we gain more detailed observations, until we can map gas outflow in real time and correlate it with trajectory changes, some uncertainty remains. So what do these three objects tell us about the broader population of interstellar visitors? First, they tell us diversity is high. There is no single type of interstellar object. Some are water-rich, others are CO-rich, some are elongated, others more spherical. Some outgas energetically, others seem inert. The galaxy is throwing all sorts of debris our way. Second, they tell us interstellar chemistry mirrors solar system chemistry. Comets from other stars carry the same molecules: water, cyanogen, diatomic carbon, carbon monoxide. As the comets, we know. The laws of chemistry are universal. The building blocks of life, if they're here, are out there too. Third, they expose detection bias. We found Oumuamua because it was bright and passed relatively close to Earth. We found Borisov because it sprouted a bright tail. We found 3I Atlas because automated survey pipelines are getting better. But for every interstellar object we catch, there are likely hundreds or thousands we miss. Too small, too dark, too fast, or simply too far for our telescopes to notice. Fourth, and perhaps most important, they tell us we need better tools. We need larger telescopes to see fainter objects. We need faster surveys to flag interstellar visitors earlier, buying time to study them. We need specialized instruments that can rapidly characterize composition, spin, and outgassing in real time as the object races past. Above all, we need luck. The universe is vast, interstellar objects are tiny, and the windows of opportunity are narrow. 3I Atlas could have slipped by unnoticed if Meerkat hadn't been listening at the right moment. Oumuamua nearly escaped detection entirely. Borisov was discovered by an amateur with a home-built telescope, not a multi-million-dollar professional survey. That is going to change. In the coming years, the Vera C. Rubin Observatory in Chile will begin operations. It will scan the entire visible sky every few nights, flagging anything that moves or changes. It's expected to find dozens, possibly hundreds, of interstellar objects per year. Instead of 3 rare visitors, we'll have a flood of data. And then, finally, we'll be able to answer the questions that have stalked us since Oumuamua first appeared in 2017. How common are interstellar objects? What are the distributions of their sizes, shapes, and compositions? Are there families, distinct categories, or is each one essentially unique? Do any of them carry life or the ingredients of life from one star system to another. Part 6. When Chemistry Meets Mystery. The detection of hydroxyl radicals from 3I Atlas on October 24th was more than a technical success. It opened a window into the chemistry of another star system, allowing us to see and almost hear how water behaves after millions of years wandering through interstellar space. Yet, as happens with every great discovery, one answer brought a dozen new questions. The absorption lines at 1.665 and 1.667 MHz are unmistakable. They mark the signature of hydroxyl radicals, OH molecules, formed when ultraviolet light splits water. The process is elementary, the same seen in comets within our solar system, in planetary atmospheres, in interstellar clouds scattered across the galaxy. Water plus ultraviolet light equals hydroxyl. Simple, yes, but simplicity in chemistry contrasts sharply with the complexity of what follows. Why was the signal detected only on October 24, and not during earlier observations in September? The obvious explanation is timing. Earlier in the month, 3I Atlas was farther from the Sun, receiving less ultraviolet light and producing less outgassing. By late October, sunlight had intensified just enough to trigger significant sublimation of water ice. More vapor meant more hydroxyl and a stronger signal. Yet its distance from the Sun had not changed drastically enough to explain the leap from silence to clarity. Something else must have occurred. Perhaps the comet's orientation shifted. As 3I Atlas rotated, different surface regions faced the Sun. If certain patches contained exposed ice, then only at a specific angle would they sublimate intensely enough to register. In September, those areas may have been in shadow. By late October, rotation brought them into direct light, igniting an outburst of activity. Another plausible scenario is the rupture of a crust. Many comets develop insulating layers of dust and carbon-rich material that protect deeper ice. When heated, these shells crack and peel away, exposing fresh, volatile layers that vaporize rapidly. A fracture like that could easily explain the sudden spike in hydroxyl emission. Or maybe the explanation lies deeper still, literally. The comet's outer layers might have contained more volatile gases, such as carbon monoxide and carbon dioxide, which sublimate earlier, while the lower strata were richer in water ice, requiring more heat but producing stronger signals once activated. The truth is likely a mixture of these effects. What matters is the precision of timing. Had Meerkat been aimed elsewhere or scheduled a week later, the signal might have slipped through space unheard. How much water does 3I Atlas truly contain? The hydroxyl lines confirm its presence, but measuring quantity is far from simple. The signal's strength depends not only on how much water exists, but also on the density and temperature of the coma, solar wind dynamics, photodissociation rates, and many other variables. Astronomers build models combining assumptions about the nucleus size, albedo, and active surface fraction. These estimates indicate that 3I Atlas vented somewhere between 220 and 2,200 pounds of water vapor each second during observation. Over several weeks, that translates into many tons of water released into space. But that is just the vapor. The solid core, a frozen mix of rock and ice about half a mile wide, likely contains vastly more. If its composition is roughly half water, the comet could be transporting hundreds of millions of tons of interstellar ice, enough to fill a small lake. And that's only one traveler. Multiply it by the countless wanderers drifting unseen between the stars, and it becomes clear how much water and chemistry move continually through the galaxy. Hydroxyl is just one molecule, water just one compound. Comets hold multitudes, carbon monoxide, carbon dioxide, methane, ammonia, methanol, formaldehyde, hydrogen cyanide. The list continues. Some are simple volatiles, others complex organics, precursors to amino acids, sugars, and nucleobases, the raw materials of life itself. NIRCat detected hydroxyl because its instruments are tuned to that frequency range, but that doesn't mean nothing else is there. Observations across the infrared and ultraviolet spectrum may one day reveal an entire catalog of chemistry, hidden within 3I Atlas's faint glow. Optical studies already confirmed cyanogen, the same molecule found in Borisov, implying that this comet too carries organics alongside water. Whether these include truly prebiotic compounds remains uncertain, but the possibility alone is astonishing. Then there are the trajectory anomalies, small deviations that refuse to fit neatly into our equations. Most comets exhibit slight, non-gravitational accelerations, caused by jets of gas pushing them like miniature thrusters. The behavior is well known and usually predictable. Yet with 3I Atlas, something doesn't quite add up. The observed acceleration is marginally greater than models of outgassing can justify. Perhaps the models underestimate the strength or geometry of the jets. Perhaps the comet emits invisible volatiles, such as hydrogen or nitrogen, producing thrust without leaving a detectable tail. Or maybe sunlight itself plays a role. Radiation pressure exerts a minute but constant push, and if 3I Atlas is unusually porous, more snowball than stone, that pressure could become measurable. There's also the unspoken thought shared quietly among researchers. Maybe something else is at work. Something subtle in the interaction between the solar wind, the comet's magnetic field, or its internal structure. The likeliest explanation remains mundane. The sum of gas jets, radiation pressure, and instrumental uncertainty masquerading as mystery. But uncertainty is where discovery lives, and that uncertainty keeps astronomers watching. So is 3I Atlas typical or exceptional? We now know 3 interstellar visitors, Oumuamua, the strange one, Borisov, the ordinary one, and 3I Atlas, which sits intriguingly between. That alone suggests diversity. Interstellar travelers are not uniform. They are as varied as the systems that birthed them. Some are rocky, some icy, some lively, others inert, some shapeless, others almost perfect spheres. And some, like 3I Atlas, carry the unmistakable fingerprint of water from another world, whispering across the void, waiting for us to listen. Part 7. The Ears of the Cosmos. Technology behind the discovery. The detection of the hydroxyl signal from 3I Atlas on October 24th wasn't an accident. It was the result of decades of technological development, years of careful planning, and the coordinated work of dozens of scientists and engineers who built and operate one of the most sophisticated radio telescopes on Earth. Let's talk about NIRCat. NIRCat is an array of 64 dish antennas located in South Africa's Karoo Desert, one of the quietest radio regions on the planet. Each dish is about 44.3 feet across, converted from 13.5 meters. Large enough to catch faint radio signals, yet small enough to transport and assemble at a remote site. Working together, the 64 dishes act as a single massive telescope with a collecting area equivalent to a dish roughly 354 feet in diameter, converted from 108 meters. But NIRCat isn't just big, it's incredibly sensitive. It can detect radio signals so faint that the total energy received from a cosmic source over an entire night would be insufficient to lift a single snowflake. We're talking about powers on the order of 10 to the negative 20 watts. Infinitesimal trickles of energy crossing hundreds of millions of miles of near-empty space, captured, amplified, and translated into data scientists can analyze. Why was Meerkat able to detect 3I Atlas when other facilities didn't? 3 factors: location, timing, and instrument design. First, location. The Karoo is sparsely populated, far from cities, airports, and broadcast hubs. That means very little human-made radio interference. Cell phones, Wi-Fi routers, FM stations all spew electromagnetic noise that can swamp faint cosmic signals. Meerkat is shielded from most of that, operating in a regulated radio-quiet zone. Second, timing. The observations were scheduled to exploit a very specific astronomical window. The comet had to be close enough to the Sun to be actively outgassing, but not so close that solar glare overwhelmed the receivers. It had to be high enough in the sky to track from South Africa, and the work had to happen in the pre-dawn hours, when the Sun was still below the horizon, but 3I Atlas was already visible. That window was incredibly short, perhaps 4 to 6 hours total. Missing it would have meant waiting until the next day, by which point the geometry would have shifted, the solar angle would have changed, and the signal might have weakened or vanished altogether. The astronomers who requested Meerkat time calculated this window with care. They modeled the comet's orbit, estimated its outgassing rate, predicted when hydroxyl production would peak, and scheduled accordingly. Not luck, planning. Third, instrument design. Meerkat was built to study radiospectral lines, the distinctive fingerprints of atoms and molecules that emit or absorb at specific frequencies. Its receivers are optimized for the band where hydroxyl lines appear, 1.665 and 1.667 MHz, within so-called L-band, roughly 1 to 2 GHz. Capturing the signal is only the first step. The data flowing out of Meerkat are massive. Every second of observing generates gigabytes of information, amplitudes, phases, frequencies, timestamps, recorded with exquisite precision. Those raw data are useless until they pass through calibration and reduction. Calibration means removing everything that isn't your target signal: receiver noise, interference from passing satellites, radio emission from our own solar system, even the radio sky's faint background glow, the soft echo of the Big Bang, plus the combined emissions of billions of distant galaxies. All of that has to be subtracted to isolate the true signal from your object. For 3I Atlas, calibration was especially challenging because the comet was faint, fast-moving, and close to the Sun. Astronomers had to use sophisticated techniques to track the object as it shifted across the sky, correcting for the Doppler effect, the frequency change caused by the comet's motion relative to Earth. The rest frame hydroxyl lines sit at 1.665 and 1.667 MHz, but motion shifted them slightly. Algorithms had to scan a frequency range, testing different velocities until the right offset clicked. Once the data were calibrated, the 2 absorption lines appeared, clear and unmistakable. Dips in the spectrum, exactly where theory said they should be. That's confirmation. That's when you know it isn't a glitch, or noise, or a data processing artifact. It's real. Meerkat isn't alone. It's part of a global network of radio telescopes studying the cosmos. When the 3I Atlas signal was detected, alerts went out to other facilities. The Very Large Array, VLA, in New Mexico, and the Green Bank Telescope in West Virginia pursued follow-ups. Arecibo, heartbreakingly, collapsed in 2020. Not everyone succeeded. The window was too tight. By the time some arrays could reschedule, 3I Atlas had slipped behind the Sun from their vantage point, unobservable until it emerged again, by which time volatile production may have waned and the signal faded. That's one of the frustrations of interstellar objects. You can't choose when they appear. You can't pause their motion while you line up every instrument. You get the window you're given. Miss it, and it's gone. Now, about the other instruments that tracked 3I Atlas. not in radio but at optical and infrared wavelengths. The Hubble Space Telescope, still operating after more than 3 decades in orbit, observed 3I Atlas several times as it neared perihelion. Hubble can't see radio lines. It works in visible and ultraviolet, but it can capture high-resolution images of the coma, tracking how it expanded and changed over time. Those images revealed structure in the tail, jets of material erupting from specific regions of the nucleus, evidence of active, uneven outgassing. The James Webb Space Telescope, launched in 2021, also observed 3I Atlas, using its infrared instruments to study the comet's thermal signatures. Infrared is ideal for comets. It reveals the temperatures of different regions. Sun-facing areas run warmer, shadowed zones run cooler. By mapping that temperature distribution, astronomers can infer how the comet rotates, where active regions sit, and how volatile production waxes and wanes over a cometary day. Webb's data also indicated complex organic molecules in the coma, compounds too heavy to sublimate where water was detected but released as dust grains carrying organics. These included polycyclic aromatic hydrocarbons, PAHs, large ring-like carbon and hydrogen molecules found throughout the universe, in interstellar clouds, planetary atmospheres, comets, and asteroids. Some researchers think such compounds mattered for life's origins on Earth, delivered by comet impacts billions of years ago. Ground-based telescopes played a role too. Giant optical observatories, such as the Very Large Telescope, VLT, in Chile, and the Keck Observatory in Hawaii, tracked 3I Atlas's brightness as it changed, looking for periodic variations that betray its rotation period. They found a spin of roughly 12 hours, slightly slower than the typical comet, but not unusually so. Spectroscopic data from these telescopes also confirmed cyanogen, Cn, diatomic carbon, C2, and other molecules previously seen in Borisov, reinforcing the idea that interstellar comets aren't fundamentally different in composition from solar system comets. The raw ingredients are the same: ice, dust, and organics forged in the molecular clouds where stars are born. And here's the astonishing part. Despite all that observing power, Meerkat, Hubble, Webb, VLT, Keck, and dozens more, we almost missed 3I Atlas entirely. Had it come 6 months earlier or later, with a slightly different tilt to its orbit, or been a touch fainter, it might have slipped through the solar system unseen. Another interstellar visitor humanity never knew existed. That should give you a feel for how limited our current detection capability remains. We're seeing only the tip of the iceberg. For every interstellar object we catch, there are likely hundreds or thousands we miss. That's going to change. In 2025, the Veracruz Rubin Observatory in Chile is slated to begin full operations. Formerly the Large Synoptic Survey Telescope, LSST, Rubin is a next-generation surveyor built to scan the entire visible sky every few nights. It has a primary mirror about 27.6 feet across, converted from 8.4 meters, and a 3,200 megapixel camera, the largest digital camera ever built for astronomy. Rubin doesn't stare deeply at a tiny patch of sky like Hubble or Webb. Instead, it takes a census, capturing wide-field images of huge swaths of the sky and flagging anything that moves or changes: asteroids, comets, supernovas, variable stars, anything transient or dynamic. And it will be extraordinarily good at finding interstellar objects. Current estimates suggest Rubin will spot between 10 and 100 interstellar visitors per year, possibly more. Over a decade, that could multiply our catalog by a factor of 100 or 1,000. Instead of 3 examples, we'll have hundreds. Instead of arguing about whether Oumuamua was typical or weird, we'll have statistical distributions, frequency curves, and full populations to analyze. Part 8. The Chemical Messenger: Composition and Origins. Every comet is a time capsule, frozen at the moment of its birth, preserving the chemical conditions of the gas and dust cloud from which it formed. When we study a comet, we're not just looking at an icy rock. We're reading a record of a star system's primordial chemistry, an archive of molecules that were present billions of years ago, as planets were beginning to assemble. With 3I Atlas for the first time, we're reading that archive from another star system. So what does the chemistry of 3I Atlas tell us about its home? Let's start with water. The detection of hydroxyl radicals confirms that 3I Atlas carries significant H2O. That alone is remarkable. It tells us that water, the molecule essential for life as we know it, is not exclusive to our solar system. It forms elsewhere, in the cold regions of other molecular clouds around other stars, and becomes trapped in comets that later wander the galaxy. But water is only the beginning. Optical and infrared observations have detected several other molecules in 3I Atlas's coma: cyanogen, Cn, diatomic carbon, C2, and likely carbon monoxide, CO, though that detection is less certain. These are all common in solar system comets, built from the same basic elements: carbon, nitrogen, oxygen, and hydrogen. Cyanogen is particularly interesting. It's a simple molecule, one carbon atom bonded to one nitrogen, but it's chemically reactive. On Earth, cyanogen is toxic. In space, it's a precursor to more complex organics. Under the right conditions, with the right dose of starlight or cosmic rays, cyanogen can react with other molecules to form amino acids, the building blocks of proteins. Diatomic carbon, C2, is even simpler, just 2 carbon atoms bound together. Its presence tells us carbon is abundant in 3I Atlas, which is no surprise. Carbon is the 4th most abundant element in the universe, after hydrogen, helium, and oxygen, the element at the heart of organic chemistry and every known biological molecule. If present, carbon monoxide is especially revealing because it encodes formation temperature. CO is more volatile than water. It sublimates at lower temperatures. In our solar system, CO is abundant beyond the CO ice line at roughly 30 AU from the Sun, beyond Neptune's orbit. Closer in, CO tends to sublimate and be lost to space. If 3I Atlas has a high CO-H2O ratio, that would suggest formation in the outer, colder regions of its natal system, far from its star, in conditions similar to our Kuiper belt or Oort cloud. A low ratio would hint at a warmer birthplace, closer in. Unfortunately, we don't yet have precise CO-H2O measurements for 3I Atlas. Observations were hard, the window short, the data noisy. As our instruments improve and we detect more interstellar objects, we'll be able to build a catalog of these ratios, comparing comets across star systems and searching for patterns that reveal whether all planetary systems make comets the same way, or whether composition varies with stellar type, primordial cloud metallicity, or protoplanetary disk dynamics. Now to the more complex organics. James Webb Space Telescope, JWST, data detected infrared signatures consistent with polycyclic aromatic hydrocarbons, PAHs. These are large molecules, ring structures of carbon and hydrogen, some with dozens of atoms arranged in hexagonal patterns like a molecular honeycomb. PAHs are everywhere. They're found in the interstellar medium, in the atmospheres of red giant stars, in planetary nebulae and in distant galaxies. On Earth, PAHs are produced when organic fuels burn. They're components of soot and smoke. In space, they form through different pathways, likely in the winds of dying stars or within dense regions of molecular clouds where carbon chemistry grows rich and intricate. Some scientists think PAHs played a role in life's origins on Earth. When comets struck the young planet, they could have delivered PAHs alongside water and other organics. Under the right conditions, with sunlight as energy or lightning discharges as catalysts, PAHs might have reacted to form more complex prebiotic compounds, precursors to amino acids, sugars, and nucleobases. Speculative? Yes, but the chemistry is plausible, and the fact that 3I Atlas carries PAHs means the delivery of complex organics from other star systems to planets in ours, and vice versa, is not merely possible, but likely common. Think about that. Every time an interstellar object collides with a planet, it delivers chemistry from another star system, if that planet has the right conditions. An atmosphere, liquid water, energy sources, that chemistry can start to interact, react, and assemble into more complex structures, perhaps even structures capable of self-replication, the first step toward biology. The galaxy isn't a set of isolated star systems. It's a network with material constantly flowing from node to node, mixing and redistributing the ingredients of life. I-Atlas is just a drop in that flow, but it's a drop we can study, analyze, and learn from. Now, what about 3I Atlas's specific origin? Which star system did it come from? As noted earlier, we can't point to a single star and say with certainty, that's home. The uncertainties are still too large. But we can make informed guesses based on what we know about galactic dynamics and planetary system formation. First, consider how many star systems lie in the solar neighborhood. Within 30 light-years, there are roughly 400 stars. Within 100 light-years, about 14,000. Most are red dwarfs, small faint stars that make up around 75% of the galaxy's stellar population. Some are Sun-like, G-type stars. A few are larger A and F-type stars, hotter, brighter, shorter-lived. If 3I Atlas was ejected from one of these systems, it likely happened during the early chaotic era of planet formation. In the first few million years after a star system is born, countless bodies, planetesimals, planetary embryos, comets, asteroids, collide, merge, and sling one another into new orbits. Some pick up enough energy to escape entirely, shot into interstellar space on hyperbolic trajectories. Our own solar system likely expelled billions of comets in its youth. Most now drift through the galaxy, invisible to us. Occasionally one returns, not because it's orbiting back, but because its random path happens to cross the Sun again after millions of years adrift. Statistically, 3I Atlas most likely came from a star system within a few hundred light-years of us. Much farther than that, and the odds of its path intersecting ours drop sharply. But that still leaves thousands of candidates. Can we narrow it further? Perhaps. If we could measure isotopic compositions, the ratios of different isotopes of elements like carbon, nitrogen, and oxygen, we could compare them with isotopic maps of different galactic regions. Distinct stellar environments produce distinct isotopic ratios depending on star formation history, molecular cloud metallicity, and contributions from multiple stellar generations. Those measurements are, for now, fiendishly difficult. They require high-resolution spectroscopy, long integrations, and targets bright enough to yield sufficient photons. 3I Atlas was too faint, moved too fast, and the window was too short. With the next interstellar visitor, or the one after, we may get luckier. In the meantime, we can speculate. Here's an especially intriguing scenario. What if 3I Atlas wasn't ejected from its home system at all? What if it was stripped? Picture this. 3I Atlas formed in the Oort cloud of its natal star system, a vast spherical reservoir of comets, loosely bound thousands of AU from the center. There it was safe, destined to orbit for billions of years. Then its star had a close stellar encounter. In dense galactic neighborhoods, especially young star clusters, such flybys are relatively common. When two stars pass near each other, their gravitational fields perturb the outer orbits of small bodies. Some objects get nudged inward and become short-period comets. Others are flung outward and escape entirely. I Atlas could have been one of those stripped bodies, torn from its home not by internal dynamics but by the intrusive gravity of a passing star. If so, 3I Atlas once circled stably, part of a comet cloud, in a system that may have hosted planets, perhaps even habitable ones. And now it's here, carrying the chemistry of that distant system through our own solar neighborhood. It's poetic in its way. Comets like 3I Atlas are messengers. They carry information not as language or symbols, but as molecules, the words and grammar of chemistry. And when we listen to their radio whisper, when we analyze their spectra, we are reading that message, translating chemistry back into understanding. Part 9. The Future of Interstellar Hunting. New Tools and Missions. The detection of 3I Atlas marks a turning point in our ability to study interstellar visitors, not because it's the most spectacular object we've ever seen, but because it represents the moment when our instruments and techniques finally matured enough to catch these fleeting events before they slip away. But this is only the beginning. The next decade will bring a revolution in how we detect, track, and study interstellar objects. New telescopes, sharper algorithms, globally coordinated observing networks, and even, for the first time in history, the possibility of launching a spacecraft to intercept one of these visitors. The biggest player in this future is the Vera C. Rubin Observatory. Rubin, which began full science operations in 2025, is built to be a discovery machine. Its 27.6-foot, converted from 8.4 meters, telescope with a 9.6 square degree field of view, about 40 times the apparent size of the full moon, can capture vast swaths of sky in a single exposure. And it does so quickly, taking a new image every 30 seconds while it methodically sweeps the visible sky from Chile. Every few nights, Rubin will have photographed the entire southern hemisphere. Each image is automatically compared with earlier frames, hunting for anything that changed. Supernovae that exploded, asteroids that shifted, variable stars that dimmed or brightened. Algorithms flag these changes, generate alerts, and beam them to astronomers worldwide in real time. For interstellar objects, this is revolutionary. Before Rubin, we relied on happenstance, someone pointing a telescope the right way at the right moment and noticing something odd. With Rubin, the process becomes systematic. Every object moving through the inner solar system will be detected, tracked, and cataloged, and anything on a hyperbolic path, moving too fast or at the wrong angle to be native, will be instantly tagged as a potential interstellar visitor. Current estimates suggest Rubin will detect 10 to 100 interstellar objects per year. Some will be large and bright, easy to study in detail. Others will be small and faint, barely visible even to the largest telescopes. But all will add to the dataset, building a statistical picture of the interstellar population. After a decade of operations, Rubin will have found hundreds of interstellar visitors. We'll know their size distributions, speeds, orbital inclinations, and rough compositions inferred from reflectivity and color. We'll finally tackle questions that are currently unanswerable. How common is water in interstellar objects? What's the ratio of comets to asteroids? Are there families, groups with shared properties that hint at common origins? Most importantly, Rubin will give us warning time. When it flags a new interstellar visitor, it will be months or even years before perihelion. That buys time for coordinated observing campaigns, telescope scheduling, and instrument planning. No more last-minute discoveries where we nearly miss the object entirely. But Rubin is only one piece of the puzzle. Other observatories are stepping up. The James Webb Space Telescope, JWST, with its infrared prowess, is perfect for detailed chemistry. It can spot complex organics invisible at optical wavelengths. It can map temperature across the coma, revealing where outgassing is most intense. And because it's in space, it doesn't battle Earth's atmosphere, absorbing or warping the signal. Radio arrays like Meerkat and its planned successor, the Square Kilometer Array, SKA, will be even more powerful. SKA, when fully built, will have orders of magnitude greater sensitivity than existing radio telescopes. It will detect hydroxyl lines from interstellar objects much fainter and farther than 3I Atlas, and it will map those lines spatially, showing how hydroxyl is distributed through the coma and revealing the structure and dynamics of outgassing. Ground-based telescopes are advancing too. The Extremely Large Telescope, ELT, now under construction in Chile, will have a primary mirror about 128 feet across, converted from 39 meters. The largest optical telescope ever built. With that aperture, it will capture detailed spectra of extremely faint targets, including interstellar visitors far from the Sun. And then there's the possibility of sending a spacecraft. Since Oumuamua in 2017, multiple interception mission concepts have been floated. The idea is simple in principle. Detect an inbound interstellar object early, compute its trajectory, launch a spacecraft to meet it, and take close-range measurements. In practice, it's incredibly hard. The problem is speed. Interstellar objects move fast, typically 16 to 54 miles per second, converted from 26 to 87 kilometers per second, relative to the Sun. Reaching those velocities takes immense energy. Conventional rockets, even today's most powerful, can't do it alone. You'd need gravity assist maneuvers, skimming planets to gain speed, or advanced propulsion such as ion engines or solar sails that can accelerate continuously for months or years. One concept, Project Lyra, proposes using a heavy lift launcher, like Starship or NASA's Space Launch System, SLS, to send a small probe on a trajectory to Jupiter. The spacecraft would execute an Oberth-boosted gravity assist, diving deep into Jupiter's gravity well and slinging outward at extreme speed. With the right timing, it could intercept an outbound interstellar object, one already past the Sun and racing for deep space. Another proposal leverages a solar sail, a vast ultralight sheet pushed by sunlight. Solar sails need no propellant, only light, so they can accelerate as long as they remain close enough to the Sun. A sufficiently large sail could reach around 62 miles per second, converted from around 100 kilometers per second, or more, fast enough to catch some interstellar targets. All such plans share the same challenge. You must know where you're going years in advance. If you spot an interstellar object only months before perihelion, it's too late. You can't build, launch, and spin up a mission in time. You need an early warning system that finds visitors while they're still beyond Jupiter's orbit, giving you years to prepare. Rubin will provide that early warning. Once it's fully operational, interception missions become feasible. Imagine this. Rubin spots a new interstellar visitor inbound 2 years before perihelion. Astronomers compute the orbit, predict the path, and see that it will pass near Jupiter on the way in. A mission spins up quickly. A compact probe with a mass spectrometer, cameras, dust sensors, maybe even a tiny lander. Launched 18 months before perihelion, it uses Earth for an initial assist, swings by Jupiter for another, and then rendezvous with the object just as outgassing begins. The probe flies through the coma, scooping dust, analyzing gas, and snapping high-resolution images of the nucleus. It measures chemistry directly, not merely inferring from spectral lines, but sampling the material. It nails isotopic ratios, hinting at where in the galaxy the object formed. It hunts for complex organics, amino acids, compounds relevant to life's origins. If luck cooperates, if the target is slow enough and geometry favorable, the lander separates, descends to the surface, and cores into the ice. For the first time, we would handle material from another star system, if not in our hands, then at least in our instruments, ready for deep analysis. This isn't science fiction. It's hard engineering, demanding serious funding, international coordination, and a little luck. But it's possible. With Rubin discovering multiple interstellar objects each year, eventually the stars will align, figuratively and literally, and a mission will fly. When that happens, when we gather the first in situ data from an interstellar visitor, it will rival the moon landing or New Horizons' first images of Pluto. It will be the first time we touch matter formed around another star. And the answers we get, the molecules we find, the isotopes we measure, will transform our understanding of how planetary systems form, how chemistry spreads across the galaxy, and whether the ingredients of life are common or rare. Even without spacecraft, the next decade will be transformative. Rubin will detect hundreds of interstellar objects. JWST will dissect them in infrared. Meerkat and SKA will listen in radio. ELT will scrutinize them in optical light. And astronomers everywhere will collaborate, sharing data, comparing results, and building a massive data set that finally reveals the true nature of these cosmic messengers. 3i Atlas was a preview, a glimpse of what's coming. The radio signal, the hydroxyl lines, the coincidence with the WOW signal region of the sky, all clues. Pieces of a larger puzzle we're only beginning to assemble. And in 10 or 20 or 50 years, when we look back on October 2025 and the detection of 3i Atlas, we'll see it as the moment everything changed, the moment we truly learned to listen to the universe, not just to watch it, but to hear it, translating its chemical whispers into understanding. Part 10. Echoes in the Dark. Final Reflections. There's something profoundly human about our need to seek patterns, to find meaning in signals, to wonder whether we're alone. The detection of 3i Atlas, with its radio signature emerging from the same general region of sky as the WOW signal, touches something primal in our collective psyche. We want it to mean something. We want the universe to be speaking to us. Perhaps it already is, just not in the way we expected. The universe doesn't need to send deliberate messages to communicate. Every photon we capture, every radio wave we detect, every spectral line we analyze is information. It's the universe revealing itself, its chemistry, its physics, its history. When we learn to read those signs, when we build the instruments and ideas that translate physical phenomena into understanding, we are participating in a conversation that has been running since time began. Atlas didn't send us a message, but it told a story of water frozen in the outer reaches of a distant star system, of millions of years drifting through interstellar dark. of a chance encounter with our sun that woke sleeping ices, and of a brief moment, a window of only a few hours, when conditions aligned just right for us to hear molecules breaking under starlight. That story is every bit as extraordinary as any message we might have hoped to receive, because it tells us something fundamental about the galaxy. It tells us star systems are not isolated, that material flows between them constantly, that the chemistry that makes life possible, water, carbon, nitrogen, complex organics, is not confined to single worlds, but is redistributed across vast distances. If that's true, and each new interstellar detection strengthens the case, then life itself may not be confined to individual planets. The ingredients for life travel. They spread. They seed new worlds through comet impacts. Over billions of years, life's chemistry may have washed across the Milky Way. That doesn't say aliens are everywhere. It doesn't say intelligent life is common. It says the building blocks are there, waiting, and wherever conditions are right, atmospheres, liquid water, energy sources, those blocks may begin assembling into something more complex, something able to replicate, something that may, eventually, ask the same questions we're asking. The wow signal, that mysterious 1977 burst that never repeated, will probably remain unknown. It could have been a comet, an interstellar passerby like 3I Atlas, briefly skimming our sky and producing a fleeting radio emission. It could have been some astrophysical phenomenon we don't yet understand. It could have been terrestrial interference from a source we never identified. Or it could have been exactly what Jerry Eman felt when he wrote "wow" in the margin. Something genuinely anomalous. Something that doesn't fit into any known category. A reminder that the universe is stranger and richer than our current models can hold. The coincidence that 3I Atlas appeared in the same region of sky 48 years later is probably not significant. 9 degrees of separation on the celestial sphere isn't particularly tight, and given that we currently detect only a handful of interstellar objects per decade, it's not statistically amazing that one falls near a historically interesting patch. Even so, the juxtaposition is enough to make us think, to remind us that unresolved mysteries remain. Despite all our technology and understanding, there are still signals we cannot explain. Phenomena that resist easy classification. Questions that stay open. And that's fine. That's what makes science thrilling. Not certainty, but the frontier, the edge between the known and the unknown, where every discovery spawns new questions and every answer opens fresh avenues. Atlas answered one question. Can interstellar objects produce detectable radio signatures? Yes, under the right conditions, proper geometry, the right instruments, we can hear water chemistry breaking in real time. But it raised a dozen more. Why was the detection window so narrow? What other molecules are present that we haven't yet seen? Why the trajectory anomalies? Is 3I Atlas typical of interstellar objects, or another outlier like Oumuamua? And the biggest question of all, when Rubin begins detecting dozens, perhaps hundreds, of interstellar visitors each year, when we finally have enough data for real statistics, what will we learn about the galaxy? What patterns will emerge? What surprises still wait? If there's a lesson from recent years, from Oumuamua in 2017 to 3I Atlas in 2025, it's that the universe has an endless capacity to surprise us. Each time we think we understand how things work, something new arrives to challenge our assumptions. Oumuamua taught us interstellar objects can be strange, not necessarily alien, but certainly unlike our expectations. Borisov taught us they can also be ordinary, comfortingly comet-like. Atlas taught us they can speak, that they can carry their stories across space if we only learn to listen. The future will bring more voices, more visitors, more stories. Each will add to our understanding, refining models, challenging theories, pushing us to think more deeply about how planetary systems form, how chemistry spreads through the galaxy, and whether we are truly alone. Perhaps one day we'll detect something that cannot be explained by natural processes alone. A signal too structured to be chemistry, a trajectory too precise to be gravity, a pattern too regular to be chaos. If that day comes, if it ever comes, we'll be ready. We've built the instruments. We've developed the techniques. We've learned to separate noise from signal, coincidence from causality, mystery from understanding. Until then, we listen, we watch. We catalog every whisper from the dark, every anomaly in the data, every object that doesn't quite fit the models. Somewhere in that flood of information, in those terabytes of spectra, images, and timing residuals, may lie the answer to the oldest question our species has ever asked. Are we alone? Atlas didn't answer that question, but it showed us where to look, not in deliberate transmissions or obvious beacons, but in chemistry, in molecules that travel between stars, in ices and organics that may seed worlds with the ingredients for life. The next interstellar visitor will tell us more. And the next, and the hundreds or thousands Rubin will uncover in the coming decade. Each one a data point, each one refining our picture, each one bringing us closer to knowing whether the chemistry we detect is common or rare, whether life's ingredients are everywhere or nowhere, whether the universe is full of voices we're only beginning to hear. The 3I Atlas signal faded as the comet slipped behind the sun and back into interstellar dark. It's gone now, racing outward at about 26 miles per second, converted from 42 kilometers per second, carrying whatever chemistry it retains toward another star system it may reach in 1,000,000 years. We had one chance to listen, a narrow window when geometry and technology aligned. We heard hydroxyl breaking under starlight. We measured line speeds and widths. For the first time in human history, we confirmed that water from another star system sounds exactly like the water from our own. Now we wait for the next. They're out there, countless icy bodies drifting through the dark. Sooner or later, another will pass close enough for us to listen. When it does, we'll be ready. Telescopes watching, algorithms working, instruments tuned to every whisper of the cosmos, translating chemistry into understanding, motion into narrative, signals into stories. And perhaps one of those stories will be the one we've been waiting for since we first looked up and wondered who else might be listening. Maybe the cosmos has been whispering all along, and only now are we finally learning to hear it.